Okay, the notes for 2-3, the remainder and factor theorems. This is something that you did in Algebra 2, so even though you may be a little rusty, it should definitely ring a bell. We're going to start by dividing polynomials. In Algebra 2, you learned that if a function f has a 0 at x equals c, and just for all intents and purposes, we're going to let that be 3. Then you learned that x minus c was a factor of f. So if c was 3, we would learn that x minus c was the factor that it came from. So the way that you got the solution of 3 was that x minus 3 was a factor. So in order to find the remaining factors, the ones that are left, if the function has degree 3 or higher, you can use division with polynomials. So we're going to look at two different methods for dividing polynomials. The first one is long division, and the other one is synthetic division. They do the same thing, just two different methods. Okay, so first of all, we're going to look at long division. So we want to be able to factor this polynomial. If we look at this, I don't believe it's going to factor by grouping. Nope. So it has 4 terms, but I couldn't factor this by grouping, and there's no greatest common factor, even though it looks like we get pretty close. If I want to factor this, I'm going to have to do division. Because the other, if this is my divisor, x minus 3 is going to be my divisor, then the quotient is going to be the other factor. It's just like when I have 24 divided by 8. If I wanted to factor 24 and I divided by 8, another factor would be 3. So division can help us get the other factor when we can't use our regular factoring techniques. Okay, so as we start using long division, we're going to create this familiar box that we've known since elementary school, and our divisor is going to go on the outside, x minus 3, and we're dividing that into our cubic, 6x cubed minus 25x squared plus 18x plus 9. And if you had any of these terms that were missing, for example, if you didn't have the 25x squared, if you had no quadratic term, you'd have to use a placeholder 0 to hold that position. Okay, you have to have in order from the highest exponent in descending order down to an x to the 0, which would be your constant. Okay, but they're all accounted for here, so let's get started. You want to think about the very front numbers and terms, So yes, we're putting x minus 3 into this cubic, but you want to consider those front runners. You want to say to yourself, what would I put on the top up here so that when I multiply around, I get 6x cubed, because when I subtract, I need them to cancel. So that's our thought process. Now let me go back. Okay, so what do I put up here? What times x would give me 6x cubed? Well, that would be a 6x squared. So as I multiply around to the x minus 3 and I distribute the 6x squared times x gives me 6x cubed, and 6x squared times a negative 3 gives me a negative 18x squared. Now be careful, because you are subtracting these two quantities, and you are subtracting each term. So one thing I like to do that works for me is I change this to addition of the opposite of each term. And now I just think about adding them. So 6x cubed plus a negative 6x cubed cancels, and that's exactly what we want to happen. A negative 25x squared plus 18x squared gives me a negative 7x squared, and then we bring down the next term. So then I add the 18x, and I go again, repeating that process. What can I put in the top in my quotient so that when I multiply around, I get a negative 7x squared? That's the thought process. So let's back up now. Undo that and think about this. What times x is negative 7x squared? Well, that would be a negative 7x. and I'm going to multiply that to x minus 3, so I get negative 7x squared plus 21x. Now again, I am subtracting those. So I'm subtracting. I'm going to change this to addition of the opposite of each term. So negative 7x squared plus 7x squared cancels, and 18x minus 21x is negative 3x, and now I'm going to bring down the 9. And I repeat this one more time. What can I put on the top that when I multiply around, I get a negative 3x? Well, that would be a negative 3, and I'm going to multiply that negative 3 to x minus 3. So I have negative 3x plus 9. Now those are identical, so when I subtract them, everything cancels. So my final answer, my other factor, actually let me move that up. My other factor is 6x squared minus 7x minus 3. This is another factor. However, does this trinomial itself factor? Are there two things that multiply to give me negative 18 that add up to give me negative 7? Well, there are. Negative 9 and positive 2, negative 9 and positive 2. So let's factor this. I'm going to use the divide and squeeze method. However you factor is up to you. You should be good at factoring at this point, so you can do whatever method works for you. So I'm going to put my x minus 9 and my x plus 2. And then I'm going to go and divide each of these. Oh, didn't mean to do that. I'm going to divide each of these by 6, the coefficient. So what I want to do is reduce these before I squeeze the 6. Let's reduce the 9 over 6 becomes 3 over 2. And 2 over 6 becomes 1 over 3. And now I'm going to squeeze that 2 in front, so 2x minus 3. And in the next one, I'm going to squeeze that 3 in front, 3x plus 1. And now this factor breaks down into 2 more. So if we want to factor this completely, the direction said to factor completely, my final answer would be the x minus 3 that they gave us originally, the 2x minus 3, and the 3x plus 1. Okay, and that is your final answer, factored completely using long division. Okay, so polynomial division, it's division just like you've known since elementary school, but now we're doing it with polynomials. But the concept of division, what the quotient is in relation to the remainder, in relation to the divisor, in relation to the dividend, those all still remain the same. So to explain some of the mess that seems to be in this gray box, we're going to break it down using just an elementary division problem, and hopefully this notation will just fall into place for you. So polynomial division says this: if you have f of x and d of x, and they are polynomials so that the degree of d of x is less than or equal to the degree of f of x, okay? So that means you are dividing by something that is a smaller degree than f of x, your dividend, just like we did here. X to the first was a smaller degree than the 6x cubed, okay? So they're saying if that's the case and d of x does not equal 0, there are unique polynomials q of x and r of x such that the following is true. Now, q of x and r of x are going to stand for your quotient and your remainder. So the concept of basic division holds true with polynomial division. So we have f of x divided by d of x. So let's put some numbers with this. Let's say I have 21 divided by 6. Actually, let me move that down a little bit. Give myself some more room. 21 divided by 6. So that's going to equal the quotient plus the remainder over the divisor. So think about when you did this in middle school and you turned this improper fraction into a mixed number. You thought about it kind of like this, the dividend and the divisor, okay? So 6 goes into 21 3 times. That's my quotient. I get 18, and when I subtract, I get 3. That's my remainder. What did you do with your remainder? You put it over the 3. Oops, sorry. You put that 3, the remainder, over the divisor. So, erase that Q. So when I do the division, I would have 3 and 3 6. So what this is saying is that, oh, hold on. It keeps going away. Sorry, guys. So what this is saying is that when you do this division, I can't seem to get it to stay, that if you had f of x, which was your 21, divided by 6, it would be that quotient of 3 plus the remainder of 3 over the divisor, which is 6. And we know that that would be 3 and 3 6, or 3 and 1/2. So they're setting up the same concept with polynomials as you did with elementary school division. Okay, so I'm going to erase this now. Kind of looks a little messy, and we're going to go to the next way to look at it. Again, f of x, another way to look at it, or, right, f of x is equal to d of x times q of x plus r of x. So this means, for example, our 21 would equal the divisor times the quotient plus the remainder. So when I did that 21 divided by 6, the quotient was 3, the remainder was 3, and the divisor, which it doesn't show up in this one, but is 6. So 21 does equal 6 times 3 plus 3. 18 plus 3 is 21. So again, hopefully now some of this notation that looks a little intimidating, if you could stop and think about it, it all makes sense, and it does all fit the same mold that you're used to. Okay, so we're going to do some more division. This says to be sure to write each polynomial in standard form. That is critical, that it's in standard form. Our exponents have to go in descending order, and use zeros as placeholders for any missing powers. All right, so let's get started with these examples. I'm going to divide by 3x plus 2. There's my divisor on the outside. And on the inside, 9x cubed. I do not have a squared term, so I need to put plus 0x squared minus x minus 3. So again, think of these front numbers as we start to think about the quotient. What can I put at the top in my quotient that when I multiply to 3x, I'm going to get 9x cubed? Well, that would be 3x squared. And I'm going to multiply all the way around. 3x squared times 3x is 9x cubed, and 3x squared times 2 is plus 6x squared. Then I subtract, which remember, I'm going to change this to add the opposite. So the 9x cubes are gone. 0x squared minus a 6x squared is negative 6x squared. I'm going to bring down a negative x and repeat the process. What can I write in my quotient as part of my quotient that when I multiply to 3x, I get negative 6x squared? Well, that's going to be a negative 2x squared. I'm sorry, negative 2x. And so I multiply around, and I get negative 6x squared. And then I have negative 2x times 2 minus 4x. So as I change my subtraction to addition of the opposite, this cancels, and I'm left with 3x. I'm going to bring down a minus 3. Okay, So I'm running out of room. I'm going to shrink this down just a little bit so I can continue on. Okay. All right, so now I have 3x minus 3. What would I put on the top so that when I multiply, I get 3x? Well, that would just be a 1. So I'm going to add 1. Then I multiply to 3x plus 2, and I get 3x plus 2. And I'm subtracting, which I'm going to change to add the opposite. 3x's cancel. Negative 3 plus a negative 2 is a negative 5. And so again, what do we do with this remainder? We put it over the divisor. So minus 5 over 3x plus 2. Okay, so as we polish this up and put our final answer, my quotient is 3x squared minus 2x plus 1 minus 5 over 3x plus 2. And that is our answer for example 2. Okay, let's look at example 3. I have x squared minus 2x plus 7. So let's write this out here. X squared minus 2x plus 7. And my dividend is 2x to the 4th minus 4x to the 3rd plus 13x squared plus 3x minus 11. All my variables are accounted for. 4, 3, 2, 1, and 0. So what multiplies to x squared to give me 2x to the 4th? That will be 2x squared. So as I multiply around to that trinomial divisor in the front, 2x squared times x squared is 2x to the 4th. 2x squared times negative 2x is negative 4x to the 3rd. And 2x squared times 7 is plus 14x squared. And we're going to subtract, which is add the opposite of each of these. So 2x to the 4th cancels. Also, 4x cubed cancels, and I'm left with a negative x squared, and I bring down a positive 3x. Now, I also am going to bring down, let's see. What I need is to figure out what I need at the top so that when I multiply, I get a negative x squared. Well, that would be a negative 1. So negative 1 times x squared is a negative x squared. Negative 1 times negative 2 is a positive 2x. Now, here's what we need to realize. With this, I have negative 1 times 7, but I don't have a constant. So in this case, I am going to also bring down the negative 11 so that I can subtract and have like terms. So my subtraction of these two polynomials is going to change to add the opposite of them. The x squareds cancel out. I get a positive x minus 4. And there is nothing left to bring down, so this is my remainder. Kind of weird, but this is my remainder. So it is positive, and it's going to go in the numerator, x minus 4 over x squared minus 2x plus 7. So to polish this up, my final answer, when I divide, is 2x squared minus 1 plus x minus 4 over x squared minus 2x plus 7. Okay, so that is long division, and maybe a little rusty on it, but it should be rather familiar. Now we're going to look at synthetic division. So synthetic division, if you remember anything about it, you probably remember loving it. It is definitely a shortcut, as it says right here, for dividing polynomials. But the key is, guys, don't forget, you cannot always use synthetic division. You can always use long division. Synthetic division is only good for a linear factor in the form of x minus c. So we could not have done example 3 with synthetic division because you need a linear factor, and that's quadratic. Okay. Once again, you need to make sure you use placeholder zeros for missing terms. And if you are interested, on page 111 in your book, the way that synthetic division is derived from long division is all laid out for you. So if you want, you can go check that out on page 111. Okay, so in synthetic division, we're just going to run through the steps again, and then we'll practice. So step 1, you want to write coefficients in standard form. Okay. And the 0, which means the x-intercept, not 0, as in the number 0, in the box. Okay, and if you're forgetting what the box is, we'll show you here in just a minute when we start our first one. Okay, that's kind of laying it out, getting ready to do the actual process. So as we begin the process, we are going to drop down, drop the first coefficient down, multiply the 0, and by that I mean x-intercept, to the coefficient, and write it under the second coefficient. Okay. After that, let me change colors so they don't run together too much. So step 3, we're going to add that product that you just got to the second coefficient. Once we've done that, we're going to repeat these steps until finished. Okay, so there they are written out for you, and this will probably come rushing back to your memories as we start to do this. So we're going to divide 2x to the 4th minus 5x squared plus 5x minus 2 by x plus 2. So the way that I write some of these symbols might be a little different than what you've seen in the past. It doesn't matter. If you want to use what worked for you back then, you go right ahead. So this is the little box that we put the 0 in. If x plus 2 is a factor, then negative 2 is the 0 that's related to that factor. So negative 2 goes in the box. Then we're going to list the coefficients in standard form. So you want to make sure that these exponents go in descending order. 4 and then 2 and then 1. But I am missing an x to the 3rd, so I'm going to need a placeholder 0 for that. So let's write these coefficients. Okay. Now, I usually go ahead and put the ending box right there at the end. This is where the remainder goes, often to be confused with the constant, but it's not. The very last number is what's left over. It's your remainder. Okay, so now we start the process. We're going to drop down the first coefficient. Then we're going to multiply the 0, which is negative 2, to that coefficient. We get negative 4, and we're going to write it under the second coefficient. Now we're going to add that product of negative 4 to the second coefficient. So 0 plus negative 4 is negative 4. And we repeat that process. So negative 2 times negative 4 is 8. I'm going to write that under negative 5. and add, I get 3. 3 times negative 2 is negative 6, goes underneath the next number. I add, I get negative 1, and negative 2 times negative 1 is a positive 2, and I get a remainder of 0. So I've divided. Well, what's my quotient? If you remember, these numbers right here are the coefficients for your quotient. Whenever you divide, if you started with a 4th degree, my quotient will be for 1 degree less. So the 2, negative 4, 3, negative 1 are they're coefficients for a cubic. So my quotient would be 2x to the third minus 4x squared plus 3x minus 1, and there's no remainder. So this is my quotient. It's my answer for when I divided. Okay, let's look at B. So letter B, this one here may give you the difference between an Algebra 2 synthetic division problem and a pre-calculus synthetic division problem. Because the number that is going to go in the little box here is not 3. You have to set 2x minus 3 equal to 0 and find the 0. It is 3 halves. That may not thrill you, but it is what it is. So 3 halves is the 0 that we're going to use. Now we're going to list our coefficients in standard form. So 10, negative 13, 5, and negative 14. We're not missing any coefficients. Again, this last box here will be my remainder. And let's get started. So I'm going to drop down the 10. So 10 times 3 halves is going to give me 15. Negative 13 plus 15 is 2. Times 3 halves is just 3. 5 plus 3 is 8. 8 times 3 halves is 12. And negative 14 plus 12 is negative 2. So my quotient would be 10, no, sorry, whoops. I mean, it is, but I forgot to list. These would be coefficients for an x squared term, x squared polynomial function. So my final answer would be 10x squared plus 2x plus 8 is my coefficient, my constant. It's getting late. And then my remainder is negative 2, so I'm going to put that over my divisor, which is 2x minus 3. And that is my final answer. Okay. So we have long division, we have synthetic division. Now, along with synthetic division, there are a few more uses for it, and these should be a little familiar as well. The remainder and factor theorems. So first of all, the remainder theorem. This says if you have a polynomial f of x and it's divided by x minus c, so let's say it's x minus 3, the remainder r, so the remainder, the thing that goes in the little box, as I pointed out in the last two problems, that is the value, if we're talking about, or that's the value of f of c, and if we're talking about 3, the remainder is the value of the function at 3. So using synthetic division, we're now going to evaluate a function, and we're now going to call this synthetic substitution. So the process is the same, we're just looking for a different result. We're going to use the result in a different way. So this is, this will give the same as direct substitution, when you directly substitute in an x value. Okay, so let's take a look. The number of tickets sold during the FMHS football season can be modeled by this cubic. X cubed minus 12x squared plus 48x plus 74. X is the number of games that are played. So use the remainder theorem to find the number of tickets sold, which is my T of X, during the 12th game of the season. So when X is 12, when they've played 12 games. So I really want T of 12. Now typically you would just directly substitute the 12 in for X and solve. But here's what we're going to do. We're going to use synthetic substitution. In the initial box, we're going to put a 12, the value that we're looking at, the X value. Then we're going to list the coefficients. 1, negative 12, 48, and 74. The answer is going to be the remainder. That's why this is the remainder theorem. So when we get that answer, that will be the number of tickets sold during the 12th game. So let's see that. All of these now represent the answer to a division problem or a quotient, but I'm not looking for that right now. So we need to get to the end though. Drop down the 1, 12 times 1 is 12. When I add, I get 0. When I multiply, I get 0. When I add, I get 48. 12 times 48 is 576. And when I add that to 74, I get 650. And that is the number of tickets sold. So T of 12 is 650. Again, not the way that you're used to doing it, but it's another use for the synthetic process. We call this synthetic substitution. Okay, last page. If you use the remainder theorem to evaluate, like we just did, and the result is 0, so this means you get no remainder. Well, I want you to think about what that means back in the olden days. If you did, let's say 32 divided by 4, that goes in 8 times with no remainder. What did that mean? It meant that 8 was also a factor. If you did not have a remainder, your quotient was another factor. The same concept works with polynomials. So if you evaluate x equaling c and you get 0, you know that c is a 0 of the function and x minus c is another factor. And that leads us to the factor theorem. And here's what that says. It says that a polynomial f of x has a factor x minus c if and only if f of c is 0. It has no remainder. So let's see what this means. Use the factor theorem to determine if the binomials are given factors of f of x. Well, what does that mean? If they're factors, 0 equals the remainder. So that's what we're looking for. Use the binomials that are factors to write a factored form of f of x. So let's look at example A. I have a quartic, 4th degree, and I want to know if x minus 1 and x plus 3 are factors. So I'm going to test them. The first one I'm going to use is x plus 3. So in my little box, the 0 related to that is negative 3. So my coefficients are 4, 21, 25, negative 5, and 3. Why did I put plus 3? Sorry. Just kind of a little confusing. Okay, so in this box at the end, I'm looking for 0 to show that it's a factor. So let's see what we get. Drop down the 4 times negative 3 is negative 12. 21 and negative 12 is positive 9 times negative 3 is negative 27. Add to 25, I get negative 2. Multiply to negative 3, I get 6. Add to negative 5, I get 1. Multiply to negative 3, I get negative 3. And when I add, I get 0. So what does this mean? It means that, yes, x plus 3 is a factor because r equals 0 right there. Okay, Now, we have another one. So x plus 3 checks out. But what about x minus 1? So let's do this. I'm going to use 1, and I'm going to give you a little hint. You can use these coefficients right here. Since this is a factor, I can use these. I could go back and use the original coefficients, but I can also use these that I just got because I know these come from another factor. And let's see what I get. Let's see if x minus 1 is a factor. Drop down the 4. 1 times 4 is 4, plus 9 is 13, times 1 is 13, plus a negative 2 is 11, and 1 times 11 is 11. When I add, I get 12. So the answer here is no. X minus 1 is not a factor. Okay, so if I want to write this in factored form, here's where I'm at. I'm at x plus 3. Yes. Oh, and this is my f of x function, sorry. X plus 3 times, and then I use these coefficients. 4 x to the third plus 9x squared minus 2x plus 1. Because again, if I started with a 4th degree, the first time I do division, I'm down to a 3rd degree. Okay, so this is the factored form of f of x using synthetic division to also prove if we have a factor or not. All right, let's try b. I would actually advise that you pause this and try b on your own and see what you get. Okay, let's test negative 5, or x minus 5. So the 0 related to that would be 5. I'm going to write my coefficients, 2, negative 1, negative 41, and negative 20. Let's do our synthetic division. Drop down the 2, times 5 is 10, plus negative 1 is 9, times 5 is 45, plus negative 41 is 4, times 5 is positive 20. So yes, we can say that x minus 5 is a factor. Okay, what about x plus 4? So the 0 associated with that one would be negative 4. And I can, since I know that 5 worked, gave me 0 as a remainder, I can use the 2, 9, and 4 and see what I get. Or I could have gone back to the original coefficients. So drop down the 2, times negative 4 is negative 8, plus 9 is 1, times negative 4 is negative 4, and I get 0. So again, yes, I know that x plus 4 is also a factor. So if they want this in factored form, we have the x minus 5. Oh, and this is f of x. I always forget that part. We have the x plus 4, and I'm going to take these last coefficients here, the 2 and the 1. As we started with a cubic, we worked our way down to a quadratic with the 2, 9, and 4, and so the 2 and 1 belong to a linear. So this would be 2x plus 1, and there we have that cubic in completely factored form. Okay. So to summarize this page, to summarize the remainder theorem and the factor theorem, if R is the remainder obtained after synthetic division of f of x by x minus x, then the following statements are true. R is the remainder of f of c. If R equals 0, so there's no remainder, then I know that x minus c is a factor. If R equals 0, then C is an x-intercept of the graph of f. And also, if R equals 0, then x equaling c is a solution of f of x equaling 0. So let's go back and just repeat those with a number involved. So if you are dividing by x minus 3, okay, then the following statements are true. R is the remainder of f of 3, okay? If r equals 0, then x minus 3 would be a factor. 3 would also be an x-intercept, and 3 would be a solution. So that kind of summarizes the remainder and factor theorems. Also synthetic and long division. So hope that all makes sense. If not, feel free to ask me some questions.